for coming. I'm Glenn McCrae at the Transportation Research Center, and we're really happy to have Dr. Ting with us today and to talk about an area that I know absolutely nothing about. So as with most of your research that I took a look at, except that it really seems fascinating, the work you're doing, the expanding across the different types of materials, and particularly things like blades for wind generators, and the expansiveness of your research and the work that's done. I was thinking we should have brought the UAV over so you could start doing an analysis on how stable that is and how many fractures we're going to have.
Well, I'd like to.
Eventually. So, I don't know if, Brian, you'd like to
Sure.
do a formal introduction?
Amanda invited you here, but Amanda's not here, so she had asked me to do an introduction. I'm Brian Lee, faculty member in the School of Engineering, and I'm very proud and happy to introduce our guest, who is a new colleague of mine in the School of Engineering. He's doing some very exciting research on materials, one of which that he will present to us today, materials and structures. He has a very interesting background from various places, doing his undergraduate in civil engineering at Haozhong University of Science and Technology in China, and then after that worked for the China Railway Bridge Institute as an engineer there, before going back to grad school at Haozhong. And then he then moved on to Princeton to do his PhD. Between Princeton and here, he was working at Oak Ridge National Lab, which is where he was working when we snatched him up to be our new colleague. So very happy to have you here. If I missed anything, please let us know, but please go ahead, Ting.
Okay, yeah. First, I should thank you all for giving me a chance to have a presentation here. This is a really nice place. I think Jacob and I already had a very good communication before the presentation. He showed me a link how to install the Microsoft Office 2013. I really appreciate it. And then the interest. I pick up this day because it's a Friday, right? And I'm in communication. But I forgot one important thing. Today is my wedding anniversary. My wife just told me this morning. I said, "Oh my God, I'm going to have a presentation in TRC." So I said, maybe it's a very. I just try my best to have make the presentation today very interesting. And the other thing here is, as being said, I do from the topic-wise, I do different things. Some of the wind turbine blades, some of the marble in the New York Metropolitan Museum. Yeah, but basically the fundamental things when I was interviewed by Brian said I do fracture. So everything has a crack. I'm interested. and the reason for me to study fracture is because I want to know why they fail and try to make them stronger. So when I moved to this region, I was very, very happy because I noticed there are so many cracks.
They're not going away anytime soon.
So and I said, okay, it seems that I have some job security and I need to do something about it. And then I said, okay, so we have a transportation research center, and I checked that there are so many good facilities there. But the good thing is, it seems there's not so many interest in asphalt. And in terms of a cracked asphalt, maybe they don't worry too much. Unless, okay, I need to do something about it. And that's why I came up with this presentation. I actually, all the presentation here, I already submitted a paper about literature about what I do in the next 50 or 60 years, how I deal with these things, and this is only part of it. So hopefully, I can just give a interaction, and this is a brief paper, and this is a very interesting one.
So maybe before you go on, we could just do a very quick round of introductions so that you know who the audience is,
Sure.
In terms of name and also what their background is.
Professor Harvey, I'm a graduate student at GRC, and I study livability in urban settings.
Michelle McCutcheon-Shore, and I'm on the outreach team here at HRC.
Karen Sentoff, I am
staffer at the Transportation Research Center. I'm getting used to that. Formerly was a civil and environmental engineering student at UVM, both in the undergrad and in the graduate program.
Glenn McCrae, Associate Director here. I'm very interested in all the cracks I ride over in my bicycle.
Jacob Leopold, I'm the Business Manager for the Transportation Research Center.
Jonathan Dowds, I'm a Research Specialist here at the DRC.
Tim P. I'm a master's student here. I do land use modeling and transportation modeling.
Sean Neely, I'm a research assistant here, and come from a background in airports, so most of my asphalt experiences on Mars.
I'm Jordan Bozeman. I'm a grad student over in the MBA program and program assistant here.
Nice meeting you all. So maybe when you have lunch, I can just eat little stuff. So today my topic is fracture experiments of asphalt mixture. Okay. So here's some like a big picture. I checked some literature in the website. So by 2013, the entire highway network in the United States is like 4,067,077 miles. So the data is shown in the below link in the blue one. You can check it, you can click it. I'm not sure whether they do some updates, but that's what I have. And then in the report by Asphalt, it says that unfortunately we have half of the U.S. roads are in good condition, but unfortunately 13 of them in a very poor condition. And most of them have a very, very bad payment system, and I think all of us have some experience how to deal with these vehicles. So here,
Vermont is worse than that.
sorry, I do have some local data. Okay, and then in terms of poor condition, as for me, the question is always what do we use to build this road system? So I checked, and fortunately. Civil engineers know that it's like a hot mix asphalt. So the short name is HMA. So when we build the roads, and basically the left bottom picture is how the multi-layer structure. We have the sub-base cost, the base cost, and then on the very top we put a payment system. So on the right bottom picture, you can see a group of people is working on very hardly on how to build this payment system. And every time when I go in the 97, I will see some of this, 93, sorry, Route 93, I will see some of these vehicles. So it's really a good experience and make me more secure about the cracks. So every year they will do the same thing. So you will know how much investment they put in this material. And this is, so what is HMA, or in the other word, the hot mix asphalt? So it's a mixture of asphalt binder and graded mineral aggregates. So they mix them at elevated temperature, let's say 150 to 166 degree. And this range is because it depends on which binder you use. So there will be a little bit of difference. And compact them to form a relatively dense pavement layer. So when we put them into an integral part, we hope they can last forever. But it seems like they can only last for a few months, especially in the winter. Okay. So here are two typical failure of the pavement materials. For the upper picture is it's called the reflect cracking. So just cracks up from one side and go across the road and to the other side. And the lower one you see so small ones, and which is very evident everywhere. So this is another kind of cracks. But anyway, both of them are the cracking of the asphalt pavement system. So in a report issued by 2007 and 2012, and this you see reference 6 there. These names are all the basically, I think not all, maybe 90% of the asphalt experts in the United States. They form an entire group to say we want to study how asphalt cracking. So they came up with this report. And then they said they come up with a conclusion that the low temperature cracking is a dominant stress of asphalt pavement, especially in cold regions. And fortunately, if you check their institute, some of them from the University of Minnesota, some from Canada, and some from the University of Illinois, UIUC. So what causes these crackings is the interactions between the thermal, mechanical, and chemical factors. There's no a single solution to account for this cracking. For example, for thermal, if you have a huge temperature difference between the daytime night or between different seasons, it can cause cracks. And also the mechanicals, we have vehicles on the roads all the time, so fatigue is something you cannot avoid. But at the same time, because the asphalt has binders such as polymers, these polymers will change their properties as time goes by. So they will change from the ductile property to like the brittle property. And all those things interact together, they can cause cracking of the asphalt. There's no simple solution. But interesting is, there's no agreed experiment right now to evaluate the low temperature cracking. That's why I summarized all of them today and try to see what we can do. So here are some components of the asphalt mixtures. So first one is the asphalt binder. You see the right top picture. And basically, the asphalt binder can be obtained either from industry or nature. There's a lake, very famous asphalt lake. If you just put asphalt lake into nature, into Google, it will tell you where the location is, and the entire lake is formed by like the ancient history geological movement, and it's all asphalt. And then the other part is the aggregates. As we see here, we have like fine and coarse aggregates, and basically different sizes of particles, stones, or sands. So, but when we put them together, we also instead have these materials. There's one thing we cannot avoid as air holes, so that's like the vacant space between them. And finally, if we want to improve some of the property, we may add some like polymer modifiers to modify the property of the binders, or we also put fibers to bridge cracks, and sometimes the recycled rubbers from the vehicle industry to increase the property. So we have all these things here. And then here's some of the imagery and what's the edge, how mixed asphalt look like. So basically, this four images shows us like the different size distribution of the aggregates. And then if you see from the gradient in the right picture, you see like the gradient of the aggregates can change from very large to very small. This is not a scientific description, but I just said so you can see the gradient. Okay. So here, so in terms of like a engineer or like a scientist, if we want to study this asphalt mixture as an entire hypothesis, we need to have some models. And then these models should cover like the material property at different scales. For example, if we start from the this one. If we start from the macro scale, okay, so let's say this hypothesis. Then we dig out small part and zoom it in, and we see that we have stones, which are aggregates, we have mortars, which are binders, and we have voids, right? So basically, most of the time, we'll stop here. But if we just go one more step further, we take this mortar out and see it. So we see like these small sands, and we see the mastic. So what are there in the mastic? If we just get one more step, we see that there are fillers, the mineral fillers, and also the bitumen. Basically, this bitumen is the primary component of asphalt. And if we just look at the bitumen microstructure, we saw that it's composed of like both asphaltenics and maltonics. So this basically goes to the chemical structure of this material. So, and then what are the major components of this asphaltenics and maltonics? Basically, the asphaltenics are these black ones. Maltonics consists of resins, aromatics, and saturates. These two have larger molecular weight, and this two has lighter molecular weight. But so basically, this ring shape of the asphaltenics depends on the ratio between this one and this one. Sometimes it's disconnected, sometimes it's ring. Okay. Then let's say if we want to study like the material properties of these asphalt mixtures, we need to know where we get specimens. That's very critical, right? So for the first one, sometimes we have so many rows and so many rows. So what we do for the few specimens is we just got this cold drill machine and take the cylinder sample out. So this is one cold drill machine. But in the same time, if we have different formula for the asphalt mixture, we want to know the property before we put them into practice. So we make them in the lab specimens. So we use this gyratory compactate machine. So basically, you have a cylinder, and then you put the mixture inside, and then you start the machine, And when it rotates, finally, this is your final product. Okay? So if we look at both this and this, what's the similarity between these two? Geometry, right? You have the cylinder geometry. Sometimes the cylinder geometry can be a very important, like the factor for the experimental development. Okay, so here, right now we know we get the specimen, and then we want to know how the crack grows or how the crack formulates, initiates. So basically, there are three basic fracture modes here. The first one is mode 1 is called opening, which is something like this. You have like tensile force on both sides and tear it apart, right? This is a very straightforward one and a very most dominant one. The second one is called in-plane shear, sliding. You have two things, and you slide into different directions. You have this sliding mode 2. And for the third one, if you have two fingers and each finger moves at different directions, the crack will go a subnode to the moving direction of the object, right? So this is called out-plane shear. So basically, these are the three basic modes of cracks, how we describe it. And in reality, the crack never happens in like either mode 1 or mode 2. It happens in a combination of tensile and shear. So it's either mode 1 plus mode 2 or mode 1 plus mode 3. Okay? But mode 1 is the dominant one. So for the mode 1 test, there's a few like primary tests. For the first one, it's called the single edge notch beam. So you have this beam test. If you don't have this 3-point bending test, 1, 3, 1, 2, 3. So what we do is we put a notch here so the crack will grow along this notch direction. Right? So the second one is called the semicircular bending. Instead of using this rectangular one, they use this semicircular one, and they also put a notch here. The crack will also grow in this direction. And the third one is they get like this shape, and then they carve into a notch, and then there are two holes here. So they just tearing apart these two holes, the crack can also close this one. So somebody may ask, why do you need so many different tests? So okay. Let me just give them. The first one is called the SEMD. This is a test originally used in mechanical engineering, and it was adapted by the AST, American Standard Testing and Methods Association, for a long time. So it was used for metals, polymers, and whatever it is for a long time. And then the asphalt industry borrowed it from the mechanical industry, and then they get these things, and you can see here. So one advantage of this is because it's a mature test, so all the like either interpretation or like the setup is very ready to get. But the disadvantage for this specimen is you see the specimen size, it's rectangular, right? But what's the specimen size for our asphalt concrete? Cylinders, right? So that means if you want to get this kind of shape, you need to invest either additional extra effort to chop into that shape, and this can also induce like further damage to the original sample. So that's why they say, okay, maybe but it has been useful for many years. And then this is like a typical load displacement. Load CMOD is like how large you apply different load the crack opening distance. So you just plot a curve, and you see here for the dot line is CMD control, and for the load displacement is basically the load line here is just one. So that means the CMOD control has a better control. You can see the curve here, right? So it's not such a huge spike. So, and then people said, okay, we have certain cylindrical samples, and we don't want to chop them too much. So we came up with this half disc. It's a semicircular bending test. So that they get one specimen either from lab or from field, they chop into different layers. So for each of them, they cut into halves, and then each of them can be fabricated into two SCB specimens. So that means for this one, this is like more easy than the rectangular shape, right? So that has been used for many years. But one argument for this specimen is that because of this wedge shape, when you put this load in this point, and when the crack grows, when you approaching to like the outer surface, it has a wedge effect. The crack will not grow and deviates. So we don't want that, and we want to know what's really happening. Okay. So here are some of the typical representative loading curves for the SCB test. So these 3 curves are for the same kind of asphalt specimens, but at different temperatures: low temperature, middle temperature, and high temperature. One thing we can notice is as the temperature changing from high to low, the peak load increase. What does this mean? We all know that when we put the asphalt binder into the mixture, it's a viscoelastic material, right? So when the temperature decreases, especially decrease from -30, 40 degrees, and then the viscoelastic properties of the material shrinks. So the composite behaves more like a solid instead of like the soft one, right? So as you increase the temperature, the elastic property of the material is more and more dominant. The peak load decreases, but you get a much relaxed curve. So in order to describe what's the fracture property in this 3, they came up with like 2 index. One is called the fracture toughness. It's related like the peak load at different temperature. So when you see as the temperature increase, the fracture toughness decrease because of peak load decrease. The other one is like fracture energy. That means how much energy we invest to create so much crack. So they just counted the area below these curves. So they found out that as you increase the temperature, the amount of energy to create the crack is more. It's because the viscoelastic property is more evident. Right? So you can see this increased trend. So because for fracture mechanics, it also originated from like the good materials, nice pigments like metals, so it's more easy to study. But for asphalt mixture, we know that they have aggregates, binders, and alloys. So the behavior in front of the crack tip is not like appealing the same situation as we described for the metals. So the people will think about, so how about the crack? How does the crack grow in these asphalt mixtures? So they put the acoustic emission in these samples, and then they do the entire test. This is low displacement test. So they capture, like if there's a 1 micro crack, they will count once. So basically this tells us like how many counts they get for this entire process. And then they analyze like this count versus load curves. They divide the load curve into 4 stages. In stage 1, it's almost like linear elastic. You can do loading and come back to the same place. And for the second stage, you get from this end of the linear elasticity to the peak load and before the peak load. And basically in this period, the inelastic behaviors occur more and more evident. And in the third stage, basically it deviates from the peak load to the rest of to like maybe half or maybe 60% of the peak load. And in this area, if you check the counts here, you see like a significant of event count occurs. That means a lot of micro cracking happens at that time. And finally, for this part, even when you go past this point, even the count still increase, but the load decreases so much that the materials basically lose their properties. Okay. So here's then people think we want to realize how the asphalt mixtures. We want to be remind that asphalt mixtures is going to crack. So they define an area in which they count all the energy for the event count here, and before the 95% of the peak load, and they come up with this distribution of the counts. So they summarize the size of this, and this is called fracture process zone in front of the crack tip. So basically that tells you when the crack is going to happen and when this crack is going to propagate. It's only for asphalt mixtures or like the caustic brittle materials. Then we come up with the third one. Because of the wedging effect I stated for the SCB test, so they said we don't want this wedge. We come up with these 2 holes and we tear them apart and let this crack grows. Because of this, like the similar cylindrical shapes, this one also has been adopted since 2005, and this is a very, very popular test right now. Okay. So one of these are like a representative, like the disk-shaped tension test curves, and you see here the peak load for this test. The peak load doesn't vary too much at different temperatures, but as the temperature decreases increase from low green one to the blue one, the area underneath the curve increase. That means the fracture energy increase. But one interesting about things here is, if you look at this specimen closely, you need 2 hours to apply the forces, right? So that means if you increase vary the thickness of this specimen, this is on 2D and the third dimension is orthogonal to the paper, okay? If you change the thickness of the specimen, the fracture energy you're going to observe is changing. So what's the size effect of this specimen? We don't know. And they already put a lot of effort into study. But one thing they can tell us is, no matter what specimen you use, the size of the specimen is also critical to the problem study. So we have just went over like the mode 1 test. So basically, a 3 mode 1 test. It's the SEMB, SCB, and the DCT test. So how about mode 2, the sliding one? And there are not too many tests for mode 2, pure mode 2 test only, but one of them is called the 4-point shear test. Basically, you put like a pair of loads here, but then because of like this position between these two, it can create like a sliding effect in this middle part, and then it can help to fail the specimen. So here are some of the representative 4-point shear tests. So you see here, what's the difference between this curves and the curves you saw before?
Catastrophic failure. It doesn't.
Yes. You don't have those relaxing tails, right? But you don't have this relaxing tails doesn't mean it's just the tail is too long, they just neglected. One of the reasons is for this mode 2 crack. When the crack happens, the crack process shifts from a propagation to a sliding process very, very quickly. And then your problem is becoming a crack to a friction problem. So, and more effort is needed to investigate. But anyway, we have this data, we know what the mode 2 graphs look like. So, and then, as I said, in a real condition, the crack never happens in a single, seldom happens in a single mode. So there will be mixed mode. So, and here are some of the representative for the mixed mode test. For example, in this one, in the classical SCB test, we have the notch here. But if we shift notch from here to here, so the crack here will be a combination of mode 1 and mode 2. And the other thing you do here is, instead of shifting the crack, you're just shifting the support, and you will also get like a similar effect. But the third one is someone said, okay, no, I don't want to shift the crack, just tilt it, and you will also get the mixed mode 1-2 result. And by using finite element method, we can study like different mode scenarios for this test. So similar things also happen if you shift the notch in an SEMB test from middle to the side. You can also get this mixed mode crack. You see crack here, it's not going perpendicular to the edges. But one thing about this test is, if you shift the notches too far away from the notches, the crack will not happen here. It will happen in the middle. So how can we control this? They say they know, but I don't know. Okay. So then, previously we talked about the mode 1 test, mode 2 test, and mixed mode 1-2 test. And then there are also some other, not fracture mechanics based. When I say fracture mechanics, I mean you have a notch. And these are 2 very dominant tests. And they are also, both of them are included in this year's NETC solicitation for the WMA materials. But I would let you know what they say here. Okay. So the first one is called the indirect tension test. What I do is, you have this cylinder without any notches, and then you put them into this one, and you put compression force. The specimen will go to both sides and fail. The reason for it's called the indirect tension because it's very hard to apply pure tension, like direct tension. So you use compression instead of tension and fail it in tension. It's a complicated idea, but it's indirect tension test. And because it's like the convenience of this test, it has been widely used throughout the asphalt industry, not only in the United States, but all over the world. But one disadvantage about this test is, it can not simulate how crack propagates, because as long as this specimen fails, it will go to different parts, correct? And then the other thing is the indirect tension test strengths you get from here sometimes cannot rate the specimen very well. And that's also the same conclusion based on my communication. I based my communication with the WeTrans people. Sometimes they find the test not good enough. And then you can see some of like the vertical stress versus strain. This stress versus vertical strain, and this stress versus horizontal strain graphs. The other test is called like the thermal stress restraint specimen test, TSRST. What they do here is very, the idea is very, very straightforward. They just have like this rectangular specimen, and they fix the plates here, so the plates will not move, correct? So when they will decrease the temperature in environment chamber, so that means as the temperature decreases, what will happen? Yes, and at one point when your temperature is too low, the specimen will fracture, right? Because if you decrease the temperature, the specimen is supposed to be shrink as well, but you hold them there, so it will fracture. And then that's why they get. That's the typical curve here. In the beginning, you get this stress relaxation area. That means the viscoelastic properties of the material is still working. But at some points, you see this straight line. That means the material is becoming more elastic than viscoelastic. At some point, it's just fractured. So they call this temperature the fracture stress. There's a some of stresses. But for this method, the idea is straightforward and gives some information, but one thing it cannot simulate is there's no load here. In reality, as I said, the cracking is always a combination of thermal, mechanical, and chemical reason. So this one is good, but it cannot explain all situations. So there are some other tests. They call it something like a double-edge notch tension test, wedge splint test, overlay test, and bending rheometer, SEMB test, and the micro tensile test, and compressive dynamic modulus test, and also double punch test. All of them, just like sometimes instead of putting one edges, they put like two notches, or they just have a combination of different tests. So here and these are the corresponding reference I found for this test. So here comes to my summary. So there are, in this presentation, I summarized there are different tests to evaluate the fracture of asphalt mixtures, including the single notch SEMB, SCB, DCT, IDT, and TSRST test. So for the mode 1 test, we have SEMB test, SCB test, and DCT test. And for the mode 2 test, we have 4-point shear test. For the mixed mode test, there will be a modified SEMB or SCB test. Each test has its advantage and disadvantages for specimen geometries, softening, size effect, and loading rates. And that's why they want to use all of them, and they haven't come up with a agreed experiment yet. So, and thank you. Any questions? Yeah.
So as part of your research, can I kind of come up with a suggested methods for like a standardized way to test asphalt?
Oh, if I can do that, I will be very famous. Good. So here my question is. Let me answer the question from the other way. From the presentation I showed, you think I missed something?
Yes. Well, maybe you didn't miss something, but you may not have told us something.
Yeah.
When you're testing other materials like wood or steel for construction in a building or a bridge, I can see how the connection between your test and the final structure are related. In this case, the way that I see asphalt being laid on the ground where it's continuously supported, I'm having a hard time connecting between how cracks are being formed and propagated and eventually failed in an environment where they're acting with point support as opposed to continuous support.
So this is a very good question, right? First, I'd like to answer from the problem you are talking about is like a mix of fracture and fatigue. So when you talk about the crack propagation, that means the cracks continue to grow, right? But as we all know, for the continuous pavement structure, the vehicles is where the fatigue part. So, but before the fatigue happens, there always be like a specific length of crack. So then the creek can grow. So basically, what all I do here is like the probability of this asphalt reduce the specific length of crack, and then we talk about fatigue. And when we study the fatigue, I mean, we can have another similar presentation here. There are also different tests, and what they do is sometimes they put like a bending device. They get a stripe of the asphalt mixture, and then they bend it. They bend it this way, and then to see how the crack grows. And sometimes they just get like one part supported, and then put a horizontal wheel, a single wheel in the test, and see how the crack grows. But all these things needs to have a foundation. That is, what is the base fundamental crack resistance property of this material we have? Because before we know how crack grows, we need to know how crack initiates. So that's the. I'm not sure whether I answered the question, but this is also a famous one. If I can do it.
To what degree is water and freezing of water a bigger issue in a cold climate than pressure from vehicles?
Yes. In terms, if we talk about water, that's another very difficult question. So basically, here's people. I realized a very interesting phenomenon is when they study like the cracking of asphalt, they want to sort of separate from the freeze shock process, because that process will make the material very more complicated. So as far as I know, when they do that different, if they want to involve like humidity factors, basically they put the humidity factor into some certain stand and then test at different temperature, and then put another like matrix and test at different temperature. But basically, right now, I don't think there's a thorough conclusion on how water is going to affect the cracking resistance of this material.
Is there any interest in developing porous asphalt so that it would drain itself rather than water getting sort of stuck in cracks in the asphalt?
The porous asphalt is a good idea, and I also know that there's some porous asphalt not just beside this building. But in terms of me, for the crack resistance property of asphalt, porous asphalt, this is another theory. Let me tell you, another field. Let me tell you why. If you have more holes, the water is more convenient to go through the asphalt pavement system. But you have more like notches here and there everywhere. So we need to find a balance between how many holes we have to let the water go and how many holes we have to not let the crack grow.
So do you do much testing, or can you talk about much testing in regards to the base layers? And then also I wanted to ask you about recycled asphalt, and I know that, or I've heard that used as a base layer that it's can actually be stronger than some other alternatives.
RAP is a good option, and it's also a good alternative material. So the reason why when you put asphalt, because we know we have so many like waste tiles every year, right? And then we put them into like the powders and we add them into the binders and then to increase the product. One reason for asphalt for the rubber is it's strongly dependent on the TG, the transition temperature of that material at that specific time. If the rubber, the temperature, I say you applied, the asphalt you applied at that area is proper that the rubber can still in a rubber state, it can help reach the crack a lot. But if the temperature is too low, like maybe lower than the amount area, then the rubber itself is behaving more like elastic material. So the capability it can reach the crack is not that significant. But this is an area a lot of people want to put like the RAP, especially and something like we saw the certification WMA. They also put some RAP inside. But in terms of how many or what types of rubber we're going to put inside, is still under investigation.
Are you talking about taking, like, you know, if you take the existing asphalt and then when it needs to be replaced, you grind it up, recycle it, and put it back in the same place? Is that what you're talking about?
No, I mean the tires.
Oh, tires.
Yes.
Okay. I'm talking more about taking pavement itself, and then when it needs to be replaced, recycling it in place, and then using that as a base layer for your next rehabilitation.
Seems like a good idea. Yeah, maybe someone can try it, but I haven't done it.
Okay.
I agree with you because even the polymer probably degrade a lot, but the aggregates are still there.
What I heard from airports in the Southwest that are doing this is that the properties of it, and someone was explaining it, so I'm not sure how well I'll relay it, but basically the geometry of it makes a better locking in and of itself when you're putting it back together again.
Yeah, I understand what you mean. You are adjusting the gradation of the aggregates to different slots. You are making the gradation more smooth.
Okay. Yeah. And then, so for your testing, do you do, or are you working with testing or that, in addition to testing like just the asphalt itself, you're testing asphalt in the context of different base layers, different base combos?
Then I think for the work I showed here, I haven't got to that stage, but this is also part. Any other questions?
I have a story to relay from TRB, and I doubt that this is something that's hit your radar, but I was walking through one of the poster sessions, and most of my work is on energy use or non-motorized travel or things of that nature, so I don't do a lot of material stuff. But I walked by a poster from a group in one of the Carolinas, I don't remember if it was north or south, and their poster was about using pig manure as an additive to asphalts. And apparently they found under some circumstances in certain temperature ranges, the asphalt actually performed very well. And it's a part of the world where they generate a lot of pig manure, so they were very excited about it. And I thought it was really neat that somebody was thinking about that and seeing about what that is incorporating.
So are you positing that someone should try that with perhaps cow manure?
Well,
We have enough to go around there.
Is that a new research direction?
the additives is an old topic. It's also a new one. When I say old, means people always add different stuff into asphalt. The new one is because right now, as the technology development, instead of doing like pure like formula-wise, we can understand from the computational-wise to see what's the chemical structure, we add different things instead of only doing the experiments. And this is a very, very exciting one. But I think people are still trying to do that, especially in the asphalt industry, but I believe we have more and more work to show up, either from computational or experimental side.
So you had a number of graphs that showed differences in the samples in terms of their ability to handle loads in different temperatures. So for our climate here in Vermont, is the summer months more damaging in terms of formation of cracks, or are moisture aside, if we just look at temperature alone, what is more problematic?
It's not either summer or winter. It's the changing from winter to summer.
Oh, okay.
It's a gradient. It's always a gradient.
That's right.
Yeah. Maybe I can raise the question myself.
Mm-hmm.
So in the very beginning, when we talk about the base fraction modes, we talk about how many modes do we have? Three. So mode 1, mode 2, and mode 3. How many modes do I talk for the test in this slide? Two. Mode 1, mode 2, and mode 1, mixed mode 1, 2, right? What's missing here?
3.
Yes, I like that. Thank you. According to my work, I haven't found any work related to mode 3 study of the asphalt mixtures. Somebody may say, okay, maybe this is not important, and we don't need to study it. And then I realized that someone did some similar work, and they show that how important the mode 3 is. So here is some like the two backup slides I prepared. For the first one, let me just discuss it. Someone showed that the mode 3 happens as the same significance as mode 2. And it also come up with a mixed mode 1 and 3. But this is a numerical work from final analysis, but from the experimental side, no one has any work in this area.
So mode 3, just to clarify, was the off shear, right?
Yes, out of plane shear.
Out of plane shear, but on a roadway.
Yeah.
Okay.
But then when I see this, I feel very happy, very excited, and cannot stop and come here at my anniversary day. So the reason is fortunately, I developed a method which can study the mode 1 and the mixed mode 1 3 case very, very elegantly. When I say elegant, especially for this one, it's because the specimen I use is in a cylindrical shape. So that means I don't need to chop into layers. I don't need to just chop into rectangles. What I need is just a cylinder, and then I can evaluate the mode 1 and mixed mode 1 plus mode 3. So my next step is just trying to talk to Brian more and to see is there any chance I can fully develop my idea. And this is I published a paper just how to study this mixed mode 1 and mixed mode 1 plus mode 3. And that's like what I said. I think this is also very important, and no one has done able to do some experimental work. And I believe method which I'm going to further develop in UVM can make a contribution to this area.
If temperature swings are so important, I'm wondering whether anyone has worked more at developing asphalt that doesn't have such low albedo, that doesn't absorb sunlight as much, so that it doesn't heat up as much during the day and then cool down as much at night.
This is a very, very exciting idea. Do you know what they call it? When we see the layers, either the asphalt cost, or like the sub cost, or like the base cost, right? So we see these different layers. So in other words, there's a gradient in these layers. When you talk about if there's some material which can absorb less heat, right, and then the effect from the thermal will be reduced. So one thing people are saying is because of the polymer industry they're moving so many years. They're trying to add some of the particles or some other additives in the polymers and change the property of the polymer into a gradient one. What does that mean? That means when the heat reach surface, because of the gradient property inside the polymers, it's hard for it to get inside. And this is called a functional gradient material. And that's something someone already done. And there's one thing is people always also want to insert nanoparticles or nanotubes to have this functional gradient properties. But honestly speaking, we are still in an initial stage. And that's the other thing I want to talk to Brian, the TS.
Yeah, I mean, that would have really big implications for heat island effects in cities as well. And I think mostly, I mean, someone can correct me, but mostly that seems like it's done with paint at this point, or some sort of surface treatment to make pavement less dark so that the albedo is higher. But that's inefficient, obviously.
If we can have those kind of like functional materials someday, I think it will be very, very useful in different areas.
Yeah.
And right now, I think even if someone can make it in the lab, it still be very expensive to use in the lab.
Concrete industry is probably excited about that.
So Chester, what you really want to do is you want to be able to have a seasonal control of temperature, so it keeps it cooler in the summer but warmer in the winter. And ideally warm enough so it melts your snow off and then you don't have to plow.
Yeah, but you don't want it to, you really don't want it to cool off again at night though.
Right.
You know?
Yeah.
So I think cool is probably good all the time.
All right.
We put a lot more energy into cooling degree days as well.
So how are you applying your torque in your picture there, or that's still the part that you're...
We need a top machine, and that's sitting in my lab right now.
Good.
So this is hot mix asphalt, right? V-Trans has been experimenting with at least some layers of coal.
Exactly. Warmer.
Yeah. No one has explained to me why or how. Just curious whether you know.
The HMA here, as I said, when it's mixed, it's around 150 to 166 degrees, right? So it's elevated temperature. But people say maybe sometimes when they mix, they think the temperature is too hot. So they try to add some additives or some other things into inside to lower the temperature. And then you can mix like maybe below 100 degrees. But the problem here is WMA is used, but the standard has not been formed because the amount of use is so huge. I guess even people want to put more effort into the WMA, the same task we do here for HMA, we'll be doing all again WMA. But the reason I didn't, as I talked, I noticed that for the third one and the NET system, they want to test the MA with the IDT, indirect tension, or TSRC, IST test. And I think, from my point of view, I think if we want to know a new material, we better gain understanding more comprehensive for the old one, and then we move to the new one. So, like for the HMA, the most weak cracking is still not touched. It's experimental study. So that's why I didn't get to the new one, because I think if the results you get is not that comprehensive, then the integration for a new material will also cause some new problems.
Just following up on Brian's question there, what is the supposed benefit of the warm mix as opposed to the hot mix? Why do people are interested in that?
Energy, carbon dioxide.
Great. Well, thank you very much for coming.
Thank you.